Hi everyone, today we are going to discuss about Maclaurin series and binomial series, if there is any speciality or any similarity between the two. Let's take one example. Consider 1 plus x raised to power p, where p is rational other than integer. So how do we expand with the help of binomial theorem? So first we write the descending powers of first term of the binomial, that is 1 raised to power p, 1 raised to power p minus 1, 1 raised to power p minus 2, and so on. The last index will be 1 raised to power 0. And then ascending powers of x raised to power 0, 1, 2, and so on, x raised to power p. And then we write the binomial coefficients. We are familiar with binomial coefficients as we have done in the previous unit, numbers and algebra. So PC0 is the first binomial coefficient, PC1, PC2, we will discuss about that, PC, P the last binomial coefficient. Multiply them and add them. So therefore, like we multiply these and add them one by one. So 1 plus x raised to power p is equal to PC0. 1 times x raised to power 0 is 1, so that is 1 plus PC1. X times 1 raised to power p minus 1 is 1, so that is x plus PC2 x squared plus and so on, the last term PCP x raised to power p. Now we can summarize that with the help of sigma. We can write nth term, or we can write a term before the p terms with the help of sigma like this. So we can generalize 0, 1, 2 up to, let's say, n. So n terms, so we start with sigma, and then PC n 1 raised to power, we can say 1 raised to power p minus n into x raised to power 0, 1, 2 and up to p, so x raised to power p, and then n is equal to 0 to p. Easier way to write that. Then we simplify PCn with the help of the factorial formula. So PCn is equal to p factorial by n factorial p minus n factorial, and if we simplify that, p factorial, that is p minus 1, p minus 2 and so on, p minus n minus 1 into p minus n factorial in the numerator, whole divided by n factorial into p minus n factorial, and we can cancel factorial in the numerator and denominator, and that simplifies to p into p minus 1, p minus 2 and so on, p minus n plus 1 divided by n factorial. So this we can plug in over here. So 1 plus x raised to power p is equal to sigma, n is equal to 0 to p. When we plug this, we will get p into p minus 1, p minus 2 and so on, p minus n plus 1 whole divided by n factorial into x raised to power n. X raised to power n. Actually here also we should have written x raised to power n. That's an error here. X raised to power n. Okay, now we should note that in binomial the convergence interval is magnitude of x should be less than 1. Now we'll consider series for 1 plus x raised to power p. Now we know that clearly fx is continuous and have infinite many derivatives, so we can use the derivations here. First derivative p into 1 plus x raised to power p minus 1, double derivative p into p minus 1 into 1 plus x raised to power p minus 2, triple derivative p into p minus 1 into p minus 2 into 1 plus x raised to power p minus 3, and so on and so on. Nth derivative p into p minus 1 into p minus 2 into and so on, the last p minus n minus 1 into 1 plus x raised to power p minus n whole, okay, so 1 plus x raised to power p minus n. Now these values at 0 in order to substitute, so we can, okay, so we can just make a line here and we can write these values. Okay, so value the function at 0. If you substitute x is equal to 0 is 1. First derivative at 0 is p. If you substitute x is equal to 0, we'll get p. Double derivative at 0 is p into p minus 1. Triple derivative p into p minus 1 into p minus 2, and so on and so on. Similarly, we can write the nth derivative at 0 is equal, if we substitute x is equal to 0, so we'll get p into p minus 1, p minus 2, and the last term, p minus n plus 1. Okay, so after that we use the formula for Maclaurin's expansion. So 1 plus x raised to power p, that can be done like this: the value of the function at 0, first derivative at 0 by 1 factorial into x, double derivative at 0 by 2 factorial into x square, and so on. Nth derivative at 0 divided by n factorial into x raised to power n, and so on. We plug in all these values. So value of the function at 0 is 1. First derivative 0 is p into x, p into p minus 1 by 2 factorial into x square, and so on. The nth derivative at 0 is p into p minus 1, p minus 2, and so on, p minus n plus 1 divided by n factorial into x raised to power n. If you look at these expressions, coefficients of x, they are nothing but they are the binomial coefficients. So we can write them like this: pc0, pc1 into x, pc2 x square, and so on, pcn into x raised to power n. We can generalize with the help of sigma, and we see that if you look at these binomial coefficients and this expression, they are same. Particular expression we can write like this: n0 to p, a general rule, pcn x raised to power n, and that is nothing but same binomial series. So we can conclude, so by Maclaurin series for 1 plus x raised to power p are equal. So therefore we can say binomial and Maclaurin series for this expression 1 plus x raised to power p are same, and we can write like this, or maybe in the different color 1 plus px plus p into p minus 1 by 2 factorial, or here we can write 1 factorial x square and so on up to p into p minus 1 and so on p minus n plus 1 divided by n factorial into x raised to power n. So what conclusion we can make from this these workings? Conclusion: ask yourself, is the binomial series and Maclaurin series same for every function? The answer is no. This is a particular case where the binomial series and Maclaurin series, or binomial expansion and Maclaurin expansion for 1 plus x raised to power p are equal. So we can conclude every binomial expansion is a Maclaurin series, is a Maclaurin expansion, is a Maclaurin but every Maclaurin is not the binomial. Now how we can claim this? If we know, can we think of these functions? Think e raised to power x, sin x, cos x, ln 1 plus x. These type of functions we cannot apply binomial expansion, but we can apply Maclaurin series. But 1 plus x raised to power p is a particular case where both Maclaurin and binomial are same. Another important point, Maclaurin series may have different intervals of convergence. Maclaurin series or expansion may have different intervals of convergence, but binomial expansion have a condition that magnitude of x should be less than 1.